Hi, and welcome to a tutorial that's going to explain how to do a radiation study in DIVA for Rhino version 4 using their grasshopper component. Um, so ultimately where we're going to end up today is using a component construction like this that you see on the right hand side, but I'm going to walk you through the steps for how to create this from scratch so that you understand what it's doing and what it can do. So I'm going to start by turning everything off, and I'll rebuild this. And so first thing, I have just a dummy set of geometry here. I'm actually going to change this and put it on layer 1, and we'll call that context. Oops. And then my proto building, which is just a rectangular object, I'll put that on layer 2 and call that building form. So if I make this a shaded view, you can see that I just have a really simple block sitting on a platform. So first thing I'm going to do is I'm going to bring in these pieces of geometry into Grasshopper. So I'm going to select my building, all the geometry for now, and I can either do that by selecting the geometry like this, or I can right click on my layer and click select objects. And then I'm going to come into my Grasshopper window here, and I'm going to double click and type brep. Brep, or as some people call it, brep, is short for boundary representation. So I'm going to, oops, I screwed that up here. So let me show you what I'm doing. So I'm going to select my geometry, and then I'm going to come into my Grasshopper window, and using my right hand, the right button on my mouse, I can pan around. If I use my middle button, I get this little pop-up. So I'm going to select the brep, or boundary representation, which is sort of a generic geometry bucket, and I'm going to right click and click set multiple breps. I did set multiple breps because I had actually exploded this into separate surfaces earlier. So now I've got, if I hover over brep, I can see there's 6 reference breps because there's one on the ground, and then there's 5 surfaces around the sides. I could actually delete my bottom surface, and you see that when I delete that, brep turns orange. That's because if I hover over it now, it's getting a null where that surface used to be. So I can right click on brep and go to manage brep collection, click the referenced one, and just click this delete. Obviously, if you just have the 5 surfaces initially, you don't have to do that, but just showing you how you can access the different pieces inside this brep component. I'm going to then copy and paste, so Control C and Control V. So I have a second copy of the brep, and then I'm going to select my context extrusion, and I'm going to right click on brep and set that. So when I set that, it automatically overrides what was in there before. Now I'm going to select the original one, and I'm going to call that building geometry. And then I'm going to select our context, or our base plane, and type context base. So now I know which one's which. So if I go back to my Rhino window and go back to wireframe, you can see now that if I select building geometry, it turns green, and if I select context base, it turns green. So those pieces of geometry are referenced, and I can actually just turn the base geometry off altogether if I want. So now we're going to work with the DIVA version 4 components, which, if you have it installed correctly, should look like this set of components up at the top of my Grasshopper screen. So there's a couple components for setup, and we're going to start with the daylighting grid, and we're going to put our building geometry into the G of the grid. And so what that'll do is reference each of those surfaces and put a grid on them. As an aside, Make sure that your units are set up in, well, I like to work in inches. So if you go to the Rhino window, if you click in the Rhino window and type units, it'll pull up your units, and you can switch from millimeters, which oftentimes is what your model comes in as, to inches or whatnot. It'll ask you if you want to scale the model if you're making a change. I can never do this right, so try it and then measure your model after you've made the change, and if it looks wrong, undo the change and try it again. Anyways, back to setting up our DIVA analysis. So I've created this grid, and if I hover over the S, I can see that my grid spacing is 17.716535 inches. I don't know where that number came from, but I would like to rationalize that a little more. So I'm going to double click in the out in the window and just type 24, so make a 2-foot grid, and I get that. If your building is a lot bigger than this box that I'm making, for this first round, you might try making your grid a little bigger. So maybe it's 4 feet, so 48 inches as opposed to 2 feet. And then if I do that, you can see that the grid size changes respectively. If I want to hide this splotchiness, I can right-click on Building Geometry and turn off my preview. And now I'm just seeing a nice white box with the grid on it. I'm going to go back to 24 for our purposes here. So now that I've got the grid set up, I'm going to create the simulation type that we're going to do. So for this simulation, we're going to do a radiation map. As you can see under the simulations, there's 7 basic simulation types. There's annual daylight, which we'll do next week. There's daylight factors, which we're not going to do because they're somewhat meaningless. There's point-in-time illuminances, which we don't necessarily need to do for this because we're actually going to be able to get some of that data out of our annual daylight. And then there's radiation mapping, which is what we're going to do today. The other 3, glare, radiation image, and visualization, are visualization calcs, which you should have done for this past week. I don't tend to use those as much in my work personally because I find them less useful. You can't move around in the model after they're done. It's just a snapshot, and unless you spend a lot of time setting up materials, the visualizations aren't going to look very realistic anyways. So we're going to do a radiation map. So I'm going to put that out in the canvas, and there's a number of settings in here that that are sort of hidden from view in different ways, so that we need to access. As an aside, on the grid component, if you zoom in, you'll see a little plus symbol, and you'll see that there's a number of additional settings that you can add in here. We're not going to worry about any of these for the moment, but you can come in here and add some more specifics. Most of them are going to be more useful when we get into the climate-based metrics of daylight autonomy and useful daylight illuminance, SDA, which is spatial daylight autonomy, or ASE, which is annual sunlight exposure. So for now, we're just going to leave the grid as is and take the G and put it into the grid of the radiation map component. It's also smart to give your radiation map a name, because what's going to happen is when this writes, or when you run the calculation, it's going to write some content back to a temporary folder, or to a folder on in your hard drive, and for easily being able to access that content later if we ever need it, it can be useful to have a name. So I'm going to make a panel, which I can do by double-clicking the / button, or the panel is also in basic parameters under input panel. And I'm just going to call this test run, or I'll call it SS1 test 1. I'm going to put that in my name. So the next thing we need to do, radiation mapping is going to require, we need to be able to put our materials onto our geometry and have the geometry referenced by material into this component. And so if you see this objects as list, so that's asking for all the geometry that's in the scene, but it's asking for it from with materials associated. So we actually need to come back to our setup up here and click the scene object, which will attach materials to geometry. And we're gonna copy that and make two of them. The first one, we're gonna take our building geometry and we're gonna put it in there, and then if you click this arrow, we have a number of sort of basic choices of materials. These are the standard materials that are that come with DIVA. We're not gonna spend too much time on radiance materials in this class, but if you have a particular material that you want to use or that it's important to your project, we'll get into materialization maybe next week, and you can ask me offline. For this model, we're going to just choose where is it? Outside facade 35% for our building geometry. And then for the context base, I'm going to put that into this object, and I'm going to choose outside ground 20% for that one. There are two ways which we can put these into the OBJ list. Either I can put the first one in and then hold down Shift and put the second one in, and so now we've got all those things in there. If I have a lot of these, though, that can get sort of cumbersome. So I like to use the merge component, which basically just does the job of consolidating multiple things into one. And when you put in a thing, it automatically adds another bucket for the next thing that wants to come in. And if you don't need it, you can come back and hit the remove parameter. Note that if you have an extra one in here, it won't hurt it. You can leave it like that, and it's fine. So now we have our materials in, and I'm gonna turn off that preview because our merge component will preview that geometry too. Oh, actually, I'll leave this like this. So what else do we need in here? The next thing down is the include Rhino scene. This is because in DIVA you can actually run simulations in Rhino without using Grasshopper. I'm actually not teaching that because I think the Grasshopper definition is both just as robust, if not more robust, than the Rhino base, and you can do a lot more with it parametrically once you know something about it. So for all intents and purposes, we're going to not even bother with that. You can actually zoom in and click the negative to get rid of that. The next thing we need is location. So again, like with the radiance materials, a number of cities are sort of pre-baked into DIVA, including Boston. If your weather file doesn't exist in this list, you can download it and add it as a path into this location, or put it in the same location where these exist, which is in the DIVA folder, and I'll explain that offline. The next one down is quality, which is based off of radiance settings. So the radiance engine works by setting a number of specific settings for how the calculation is performed, and obviously the higher the quality, the longer the calculation time. For now, I'm going to leave it on low, and that should be fine for initial purposes. And finally, run. So I'm going to double click on the canvas and type toggle and grab the Boolean toggle, and I'm going to plop that into the run. And now my first radiation map is pretty much ready to get going. So I'm going to double click on that, and you'll see a Windows command line pop up. And this is basically the calculation. You can see in here, oh, it's already done. We'll come back to that later. So now that I've got that done, I don't see anything. And that's because the output information, which you can hover over here, uh, the out is just showing where that information was created and stored. So this is the path on your computer to where those files are sitting. So they're in the documents, DIVA, GH data, SS1 underscore test one radiation map folder based off of that folder that we created. SE is this total solar energy captured on each of the individual surfaces that we just looked at. SED is the solar energy density received by analysis surface over the run period, which is the whole year. And then our grids. So in order to view the grids, which is ultimately what we're here for, we need to go to Data and Grid Viewer, and then plop that in. And now in the Rhino viewport, we see some colors. So let's deconstruct this a little. We can see that on the south and the roof, or the top, our solar radiant exposure is about 1,000 kilowatt hours per meter squared. On the east and the west, we see that it's a little less than that, maybe like 750. And on the north side, we see sort of in the 300s, dropping all the way down to like the 100, 200s down at the ground level. So that seems to sort of make sense, right? Like we're in Boston, and our maximum solar energy is accumulating on the south and the roof, and the east and the west are a little less, and then the north is even less than that. So we've basically now built ourselves a little engine so we can test a number of different things. So the first thing I could do, just to keep things really super simple, is if I select my building form in Rhino now and I just rotate it, let's say 30 degrees. It's automatically going to run another calc because I had that toggle set to true. If I didn't want to run it again before making some changes, I'd have to set it to false. But now that I've run it again, I can see now my southwestern facing facade has some modeling to it, and it's increased its the solar radiation accumulating on its surface. And the northwest side is also diminished, respectively. So we can already see that there's some changes being made just by virtue of a simple rotational shift. If we want to take this further, we can start messing with the angles of surfaces and how they relate to the sun. But this data is only so useful because right now this radiation mapping is over the whole year. So basically what I'm looking at is the amount of accumulated solar radiation over the entire year, which might not be as useful as if we can break that out by summer, winter. So let's go back into Rhino, or into Grasshopper, and I'm going to toggle my run to false so that it doesn't trip it when I make any changes. And I'm going to zoom in and click the plus symbol on the radiation map. And now we have some additional parameters that we can work with. First of all, if your building is not true north, or I'm sorry, if your model is set up orthogonal to the building and not to north, instead of rotating all of the geometry, you can set your north rotation by clicking on the north rotation in the radiation map, and it adds a little input value for that vector. So you're looking for degrees clockwise in plan as the location of north. If I go back and press the plus again, I can also see where I can change my radiance parameters. So this is what sort of the raw parameters looks like for how the calculation runs. AA stands for ambient accuracy, AB is ambient bounces, AD is ambient divisions, and so on and so forth. All of these settings can be found in online with documentation for what they all mean. Again, for everything we're doing in this class, you should just be able to use the standard quality options. But note that You know, the more bounces you have in a space, and the higher the divisions, you know, the smaller the surface geometry gets, the more accurate it's going to be, but also the longer the calculation is going to be. So what we want for this next pass is to add a start and end date. So I'm going to add the start date and end date. And now what I can do, oh, I'm going to turn off my north arrow. So now I've got the option of adding the start to an analysis period and the end to an analysis period. So I want to be able to run just summer and just winter separately. So I'm going to do, oh, this is asking for the month and day. So I'm going to make a panel, and I'm going to do 3/21. And then I'm going to copy that and make another one called 9/21. So now I've got my spring equinox and fall equinox. So I'm going to start by I'm going to do summer first. And I'm going to look at 3/21 and 9/21. So now I've got a picture of what the summer exposure looks like. And now, instead of just like printing an image of this, what I can do is go to params in my DIVA toolbar up top and click daylighting grid. And I can put my grid into here and right click on the grid and click internalize data, and now put that into my grid viewer, and now that's standalone. So I can make this false, switch my 9/21 and my 3/21 to do my winter, rerun this, and now pull another daylighting grid and internalize that. Grab another grid viewer, and now, oops, if I turn my summer off, I can see my winter. So I can call this winter and summer. So now I can see the difference between the winter radiation, which is very poor in the north and maybe only gets up into like the 500 or 600s on the southeast and the 300s on the north and the southwest, compared to my summer. So now I can take screenshots of this and put them side by side and sort of start to get a more nuanced understanding of how the solar radiation impacts these surfaces. Obviously, I could also make these times even smaller to look at just typical summer in June and July, or look at the winter time in the dead of winter.